Hi, everyone. So I'm going to present you first what look like a typical NFV deployment with OVS-DPDK today. So this is a typical compute node used in NFV deployment today. And on this compute node, you have OVS-DPDK on the center. On the right, you have a VM which is running an SRIOV-based VNF. And on the left, you have a VNF running on top of OVS-DPDK for the data plane interface. Just to say that today we can collocate SRIOV and vhost user-based VNF on the same compute node. And what you see is all the links are doubled, so you have bonding because in case of you have a top-of-rack switch failure, this is what is giving you the high availability from the traffic perspective. So when you have on the right a VNF running SRIOV, the bonding is done inside the VM. On the left, the bonding can be done on OVS-DPDK. So this is why bonding is a very important feature in OVS-DPDK. That said, you have two kinds of interfaces. You have the data plane interfaces on which the packets are processed, which are running at 100%, so VF0, VF1, or VIO0, VIO1. And you have also a housekeeping interface for SSH and SNMP and logs on the VM, all going through OVS-DPDK. Talking about the performance of OVS-DPDK today, the VM are pretty fat. You don't put 20 VM on one compute node. You put a handful of them. And the performance that is interesting today is PVP, physical, virtual, physical. The VM don't talk a lot to each other, to the next VM. They're talking to another compute node or to a switch. So this is typically the journey of a packet. You go through one active interface to the VM and back to the physical NIC. In terms of traffic, what does look like the mobile traffic? So if you take a chunk of 10 gigabit of telco traffic, mobile traffic, average size of the packet is 600 bytes, 4 million of packets per second, 1 million of established flow, one flow being a contract, so it's a bidirectional 5-tuple, 200 new flow created per second, 200K flow destroyed per second. So at the end, you have 1 million of flow established with 200K churn. If you have a 25 gig traffic, you multiply the number by 2.5. If you have 1 gig, you divide by 10. Now, taking a little X-ray of the compute node. So you have, as you know, DPDK is about an active loop, taking 100% of the CPU. So in OVS-DPDK, the PMD thread running at 100% are sending packets back and forth between queues that come from the physical NIC or to the logical NIC, the vNIC, the vhost user. And you have the data plane NIC, and you have also the housekeeping NIC. Okay? So in terms of requirements, we don't need a lot of speed for the management interface. So what do we need for the management interface? Because one of the constraints with OVS-DPDK is all the ports are on BR-int. So meaning, even if you have, so you cannot mix kernel and kernel OVS and OVS-DPDK. You have to go full OVS-DPDK because you just have one integration bridge where all the VM ports are plugged. So no choice. So usually people use VLAN for the traffic segmentation. Sometimes they use VXLAN, but most of the time it's VLAN. Security groups are expected to be turned on, either stateless, but they prefer stateful. Low traffic, and usually they come on a dedicated NIC because they don't want to mix user traffic and management traffic. Now, what we talk most of the time about is the user traffic interface. So the user traffic, the 4 million of packets per second. So usually that's what we use as an underlaid, it's VLAN. MPLS is often requested. We have few requests for VXLAN. But once again, in most of the deployment today, what we see is VLAN. Security groups are turned off because in order to secure properly user traffic in a telco environment, you use a layer 1 to layer 7 firewall, and typically the firewall is one of the VNF. We have your request to add some ACL to say, okay, that VM can talk to that VM. So this is something that we have the request yet, and this is something we're going to implement. And once again, so the NICs are bonded, active-passive, LACP, and often with a 9K MTU because it's easier to put the MTU to the max and then it's easier to operate. So now talking about performance.
So let's look at performance, and this is with respect to OpenStack, but also run bare on the. So this is our typical deployment topology. It's a 2-node, and you would, where the T-Rex sits as our traffic controller, you would have your OpenStack controller over there. This is a simplest deployment that we could test with. You have one compute node running T-Rex, bonded NIC coming in to the compute node and under test, which has an OVS-DPDK. This is all OVS-DPDK use cases, and coming in vhost user to the VM. VM is test PMD. Test PMD is not going to be a bottleneck. We've allocated enough CPUs for test PMD. To avoid that, we're running IPv4 traffic, no VXLAN, no QoS, everything on the same NUMA. So everything, all the VNFs, threads, vCPUs, OVS-DPDK, PMD threads, and the NIC on the same NUMA. It's an RFC 2544 test, UDP flows, and then we will add contract and measure performance with that as well, and scale up the flows. This is, we had a lot of discussion today about EMC, the exact match cache, and its impact on OVS-DPDK. Given that we are looking at 4 million packets per second, there is, for us, not a significant impact by enabling or disabling the EMC. We're seeing like 5% to 7% difference, and maybe with membership library from Intel, with 1711, we might see better. But what we're looking for, what we're seeing right now is with OVS 2.7 and DPDK 1611, and that's the platform that we're using for our next Red Hat OpenStack 12 deployment with Pike. So that's what's going to go out, and that's the performance that we have. We're running 1K, 10K, and 100K flows, and the impact on that with all of this. Let's look at that. 1K and 10K flows, baseline performance is about the same, no difference. You go up to 100K flows, then you're taking beyond 10K. If you go even 20K, 50K, 100K, you're seeing up to 50% degradation in your performance. And it looks like where OVS-DPDK PMDs are now taking a lot more of the LLC cache and with flow count. Let's look at individual features. So we start with baseline. And this is 4 PMDs, 4 hyperthreads, 2 cores, 1 NUMA node. And with baseline, no firewalls, 1K flows, we have 7 million packets per second, bidirectional traffic. And this is no VXLAN, no contract, no QoS, no LACP bonding. We have bonding, no LACP bonding. And then we have a very friendly VM, so there's no competition among the VMs right now. You add cross NUMA, you take a 50% hit. And then in your performance, you add VXLAN, you're taking a 30% hit in your performance. You add 100K flows and contract, and you're down to an 80% hit in your performance. You go down to 1.6 million packets per second. And we're talking 64-byte packets, smallest size. Let's look at 2 other features very quickly. LACP, balanced TCP, active backup. This is with LACP. And now our biggest concern is when we add LACP and it's fast LACP timer, what is our recovery time on failover? Say we break a link between on the bond and we're running traffic, 1K flows and different packets per second, and we're measuring what is the packet drop as an indication of the downtime or the service downtime. And a rough indication is we started with 1,000 packets per second, 100K packets per second, and 1 million packets per second. And we're roughly seeing between 300 to 450, 500 millisecond downtime or during the switchover from an active link to a backup link. And looking at live migration, this is a new feature that we're looking at and to measure what is our downtime. And we're moving a VNF from one compute node to another compute node. And at the same time, we have traffic, 1K flows, running at not very high packet rates, but 1 million to 5 million packets per second. And then we have an SSH session as well running to the VNF, and we're running 100 millisecond ping. And our goal is to measure packet loss for the ping as well as the 1K flows that we're running, and we need the SSH session to stay up at all times. So given this, there are some caveats here. OpenFlow pipeline is normal. Mac Learning and gratuitous are turned on. Our guest is 1 gig guest with just one single huge page, 1 gig huge page, and a few 2 meg huge pages. So this is not a typical VNF. A realistic one, you would see a lot more thrashing when this happens. And so that's what we're trying to also emulate with test PMD. That's a request that's gone to the mailing list to enable that with test PMD to do a more realistic live migration test. Again, no security groups, no QoS, no VXLAN. Adding contract could affect, the contract has to migrate as well. So that would be an impact. But given that our migration time is a QEMU measurement, it's between 12 seconds to 17 seconds, but our service downtime measured by packet drops is 100 milliseconds to 150 milliseconds. And now I'll hand back to Franck.
So, other dimensioning parameter, talking about the go live. So how many cores, how many, so what we do with OpenStack, we dedicate the first core of the NUMA of each NUMA socket to the host, to Linux, because first you have some interrupts you cannot reroute. So you have no way to run a DPDK application on the first CPU of the NUMA socket without being interrupted. So this one is sacrificed and given to the host. So at the end we have 2 cores, 4 hyperthread in a dual NUMA socket, that's the yellow partition, for the host. So on that, you run SSH, OpenStack services, disk interrupt, everything, plus OVS vSwitch control plane, the non-PMD thread. On the other core, you dedicate cores for either the VM, either OVS-DPDK. So the user is choosing how many OVS-DPDK cores he wants depending on the performance PVP he wants. So let's say we have 2 million of packets per core PVP. I want 4. I put 2 cores per NUMA socket. In terms of number of dispatcher revalidator, in this case, because we have 4 CPU, so 4 hyperthread for the host, we just have 4 dispatcher, 4 revalidator, as many as the host CPU, because having more makes no sense. In terms of number of huge pages to configure to OVS-DPDK, so there is a kind of complicated and documented formula depending on the queue size, how many NICs and everything. But basically what we do is we start with 4 gig per NUMA socket, and if it's not enough, we double, and most of the time that's fine with 4. Now, talking about the challenge on the deployment today. So when you boot a VM, the queue are so when a queues come up in OVS-DPDK with a new VM, for instance, the queue are distributed in a round-robin fashion among the PMD of the proper NUMA node. Okay, if you're on NUMA 0, so that would be for the PMD of the NUMA 0. So if you do that, how do you ensure that you balance the workload between all of the core? So you can't, because it could work if all the queue were equally loaded, but for instance, you have the SSH, the monitoring, the housekeeping queue, which will have a little of traffic, and it's even worse. Your VM can create like 10 queues and just use 2. So you have no way to balance the queue properly, just with the default algorithm. But there is one way you can make it work, is if you have way more queue than the PMD, it works. Meaning, if you use 1 PMD, just 1 PMD per NUMA socket, the workload is well balanced because you balance with yourself, just 1. In that case, but the point is, this is useful, and I've got another talk about Swisscom, and this is exactly what we use, and this is live today. So the future to remediate to this is auto-rebalancing. So the first version landed upstream, and testing is in progress. So the idea is to rebalance the queue depending on how much they are used. This rebalancing has to happen regularly because if you think about active backup, if I flap from active to backup, I've got one interface which will just, it was 100%, now it's 0%. So you need to do that regularly. And the challenge is to do that without service interruption, or at least with a minimum and something that we can measure. Final thoughts. So with OpenStack Newton, with OVS ML2 plugin, once again, without security group QoS with 1 Kflow, out of the box, you can expect with 1 core of OVS-DPDK, 2 millions of packets per second PVP. 2 millions, because you will be cross NUMA, maybe. If you're straight NUMA, you can expect still 1 core to hyperthread, you can expect 4 millions of packets per second. Because this is 1 core, because this is 2 hyperthreads, all of the queue will be well balanced. So this is kind of good. 4 millions PVP per NUMA socket. You need a little workaround because OpenStack does not support yet to specify on which NUMA socket you don't have NUMA affinity for a vSwitch. You have that for SRAV, but not for the vSwitch. This is work in progress, but we have workaround to make the boot up of the VM NUMA aware. And now, and this is where everybody wants to go, they want the performance to scale. 4 millions per core, scaling with the number of core. And you can do that. It's possible. You just need to know exactly what queue, the weight of each queue, and to repin them manually without the rebalancing. You can do that. And if something changes, you have to change it. So it's kind of very, very advanced hacking, but it's possible. So the challenge is, the good thing is we see a lot of traction and a lot of go live. We have go live. We have traffic, live traffic going on top of OVS-DPDK today. But we have challenges to accelerate this go live and the adoption. The main one is to get the performance scaling. As I said, you need a very, very thorough full understanding of OVS-DPDK, so we need more experts. Today, to go above 4 millions of packets per second per NUMA socket, you need an OVS-DPDK developer, hardcore one, to be in the loop to help for the configuration. So first thing is we need more experts. Second thing is we work on the simplification, and the queue rebalancing will really help. Also, in order to put the right expectation in the telco mind, we have, as a community, and the OPNFV vSperf is here for that, to provide the per feature impact. Every time you turn on a feature, you consume cycles and memory, but I don't care about memory right now. So you degrade your performance. So people that will say, okay, they will make their calculation about how many cores for OVS-DPDK and for their rollout, and then they will take the number without any feature, and at the end they will have 7 times less than expected, so this is not good. So we have to provide numbers per feature, so people know the cost of each feature, and they choose if they really need it. Because if it's cheap, they will enable it. Because do they really need all of the feature? That's another question. So all test cases of OP, all test cases that we develop, the CI can be reused for any vSwitch vRouter, including OVS hardware offload. Because the VM are the VM, you will not change it. The user traffic is the user traffic. The vSwitch you put in the middle can be any vSwitch. So once you have this testing framework, you can compare any flavor of OVS with, without offload, any vSwitch, anything. And you can have a fair comparison. And the good thing is OPNFV vSperf is an upstream project. So if you have any vSwitch, I encourage you to join the OPNFV vSperts. Put your vSwitch in there. There is TestPMD as a vSwitch, OVS, OVS-DPDK, and the number are published. And the test plans, the TRX, the hardware is the same for everybody. Fair comparison. And the last thing is, so some cool features still need to be coded. So if you can code the automatic queue balancing without packet drop, I know a lot of telco that would be super happy. And even if we cannot do that now, the most important thing is to have a test deployed in vSperf to measure how many packets drop, so they can choose if they turn it on, off, today, right now, while we improve. Thank you.
All right, we have time for questions. There's mics on either side, and I can also run them out to people.
Do you see SRIOV also being used dominantly in this use case, or?
In NFV?
Yeah.
Yes. Yes.
Absolutely.
So
Yes.
in terms of deployments, what do you see? More VirtIO deployments or more SRIOV deployments?
Today, it's more SRIOV.
SRIOV.
More SRIOV.
But the point is, the goal is to go to vSwitch. So we have some VNF which are already on vSwitch. This is very fine. And we want to bring them all. So this is a work in progress. And everybody wants to go to the vSwitch.
So there was a presentation in the DPDK conference yesterday about enhanced networking stack in VMware, right? Do you think that something like that here would be useful for VirtIO?
Didn't get the...
There was a presentation about enhanced networking stack, ENS, in VMware yesterday.
Yes.
Do you think something like that would be useful here for VirtIO to improve the VirtIO pole mode driver performance, where what they have done is the kernel driver, right? They have made it more, made it polling. Also the, the software switch, they have made it polling.
I see.
Maybe we can talk offline about
but
this.
the point is, my main point is also for you to understand that we will have talk about OVS hardware offload. OVS hardware offload is also a way to improve performance. So you have different ways to improve the performance. And right now we're talking about a pure software solution. In a pure software solution, we don't see a better solution than OVS-DPDK. Now, if you start to do OVS offload, you can just go with kernel and or OVS offload. But
so there's definitely room for improvement on OVS-DPDK, and all enhancements should be looked at. So membership library that was discussed today, and then there is other options as well for including not only pole mode drivers, also bifurcated drivers where we're using both. Those are all options that definitely we can look at. But what we're going out is what we have today with live with 16.11 DPDK and OVS 2.7.
Thank you.
We have time for more questions. Justin, you have one?
You'd said you used RFC 2544. That often doesn't work very well with virtual switches because it starts blasting packets immediately. So I assume you're doing something so that you warm up the caches or something before you start doing the traffic, or I was just curious how you did that.
You have a silent period between iteration with your RFC 2544. So it lets some time, and you divide by 2. So it's no, that's for sure you blast. And you oversubscribe at the beginning, but then you're under. So because you have a silent time, it's not a problem. And if you have a problem, it's because your switch has a problem, because you should recover from an oversubscribe, a temporary oversubscription.
Right, but usually what happens with OVS is because it has caches, then it takes a little while for them to get populated. So the traffic usually is really bad for a while because it's missing and it's being handled, as it's going through the entire OpenFlow pipeline. And then once those caches heat up, then the performance is much better. But if the performance of, like if you just run a typical 2544, the performance is bad because it's sort of doing the initial measurement when the caches aren't warmed up.
So,
so also we're running VSPerf version of it, and they have initial burst.
Okay, so they take that into account.
And then they stabilize, and they have a 2-minute interval where and it's customized and it's upstream. So you could definitely look at what has been done, and most OPNFV has test beds where they're running this. So you could see exactly what is being run. It's definitely RFC 2544, but it's packaged as VSPerf.
Okay, yeah, and then so they're taking into account that it's running on virtual switches, which have different characteristics in hardware.
And we have checked manually. We have checked manually that ramping up from 0 up to we had the same number as the RFC 2544, so there was no side effect.
Great, thank you.
Let's thank our speakers.